All right, let's start chapter three. Chapter three is called Numerically Summarizing Data. Um, as the name implies, we're going to be summarizing data through numbers, hence numerically summarizing, which means we're going to be focusing on quantitative data. We can't numerically summarize a category like someone's favorite pet, hair color, type of car, those types of things. So moving away from that and getting into numbers. In this chapter, this is where we kind of start using our calculator. So for this video, we'll go through some stuff that we will do on our graphing calculators. I will be using a TI-84. So if you have one of those, you'll be able to follow along. For the most part, everything I do, there is instructions on how to do it in the notes packet. So if you forget or you're not quite following along, there's instructions. And if you miss something, feel free to ask me, but YouTube is a great resource. If you Google how to do something on a TI-84, there is a very, very good chance that there is a YouTube clip that shows you exactly what you're trying to do. And some of those clips go even further than what I will be showing you. So YouTube is a great resource for being able to find out kind of what you can do with your calculator. All right, so first thing we're going to talk about, and it's not necessarily just for this chapter, but we're going to get some variables kind of situated up front so that as we start moving through the semester, we understand what those variables are. So the variables we're going to talk about is size, mean, standard deviation, variance, and proportion. And for each of these, there's a different variable that shows us whether or not we're talking about the population of something or a sample of something. So getting started, when we're talking about the population size, we use a capital letter N. So capital N means whatever number follows that, that's the size of our population. For a sample, we have lowercase n. For mean, we have this little guy here, and this is the Greek letter mu. That is our population mean. And then for our sample mean, we have this variable here, and this is pronounced X bar. The bar on top denotes that it is an average. That's what means are. A mean of something is the average of something. X is simply the variable we're finding the average of. So as we go through this course, you'll see many different variables with that bar on top. And that bar on top represents average. So we have X bar. When we start looking at scatter plots, we'll have X bar and Y bar. Later on in the book, we get into D bar, which talks about the average difference between two things. And then if you look at a calculus course where we're finding the average value of a function, that is f, which is the function, and then f bar. So there will be a bar above that. So that bar notation representing average shows up in a lot of different places. Next, we have standard deviation, which is a measure of spread, like how spread out the data is. And for population, that is our thing, and that is the Greek letter sigma. Those are both lowercase mu and sigma. Those are the lowercase versions of those Greek letters. You guys have probably seen the uppercase version of sigma before, and we'll actually be seeing it again later. It's that guy right there. That is the summation sign when we use it in math, and that is uppercase sigma. Standard deviation for a sample is simply S. And then for variance, it is sigma squared and then S squared, which shows you the relationship between variance and standard deviation. They're very closely related. Standard deviation is simply the square root of variance, or variance is the square of standard deviation. And then for proportion, we have the letter P. Lowercase p is our population proportion. And then our sample proportion is this guy right here. And that is pronounced p hat. So we'll see that in a couple places as well. All right, so now let's get into 3.1. 3.1, we're going to talk about measures of central tendency. There are 3 of them. This should be a fairly quick section because all 3 of them are things that you have heard of before, and they are mean, median, and mode. And so not a lot of new material to cover, so we'll get into it. Again, definition back from chapter 1, the difference between a statistic and a parameter. A statistic deals with a sample and a parameter deals with an entire population. All right, getting into how we find the mean of something. It's the same way that we've done it forever. We simply add up. So that is a summation, meaning we're going to add up every x value. So x sub I, each x sub I is an individual data point. So you'd have x sub 1, x sub 2, x sub 3, where each of those is, say, how fast someone ran a mile. And then you would add up all of the times of the people that ran the mile, and then you divide by how many people ran it, and that would give you the average time of those people running the mile. The only difference between X bar and mu, so the difference between a sample and a population, is going to be the variable that we use to represent that. The way we find mean does not change from a sample to a population, whereas when we find a standard deviation and some other stuff, it does. But for the most part, when we're talking about a measure of central tendency, the calculation doesn't change based on sample or population. The only thing that changes is the variable we use to describe or identify what we're talking about. All right. Using your calculator, go ahead and find the mean of that sample data or of that data. So we go through and we're simply adding So we add everything up and we divide. There are 6 numbers, so we divide by 6 and we get 20.17. So that's our average. The next question says, okay, how would we label this if it was a sample mean or a population mean? Sample mean, we would say X bar equals 20.17. And if it was population, we'd say mu is equal to 20.17. That's the only difference. On your homework, there will be some questions where you find the average of this set of data, and then it almost looks like it's multiple choice because there will be an A option and a B option, but the A option is going to say like X bar, and then there's a blank spot where you can enter the number, and B will say mu, and then there'll be a blank spot where you can enter the number. You have to determine whether the answer is supposed to be next to the X bar or the mu based on whether the data set given to you is a population or a sample. So you only have to pick one, but you have to determine which one you are finding. Are you finding a population or are you finding a sample? Next, we talk about median. Median is abbreviated either as M or as MED. So when you see MED, that's talking about the median. And the difference between mean and median, the median is the center point of the data set. So in order to find the median, the first thing you have to do is you have to organize your data. You have to sort it so it's either increasing or decreasing. Doesn't matter which one, but it needs to be sorted. If we have an even data set, so let's say there's 6 data points or 10 data points or 100 data points, if that's the case, then we find the average of the 2 middle terms. If we have an even data set, that means there's no exact middle. So we find the 2 middle terms, and then we find the average of those. That gives us our median. If we have an odd data set, so 5, 11, any odd number, then there is going to be an exact middle point in the data, and that is going to represent our median. So pause this video. There are 3 examples. Go ahead, find the median for those 3 examples, and then unpause, and we can check to see if you in fact did it correctly. All right, so looking at this first one, there are 6 different data points. which means we have an even data set. So we find the middle two. Lucky for us, this is already in ascending order, means it goes from small to large. So it's easy enough to find the two middle data points, and then we find the average of those two middle data points. So 20 plus 20 divided by 2. The median of that is 20. Then we look at the next one. So this one was even, so we had to find the average. This one is odd, which means there is an exact middle. And so we don't have to find an average. We just look for the middle one. And it is also in ascending order, so we didn't have to do anything. Now, example 3 is not in ascending order. So that means we have to put it in ascending order before we can do anything with it. So let's rewrite this. So 11, 13, 14. And there we go. It is now in ascending order, and this is even. So because it's even, again, I have to find the middle two. And because I have to find the middle two, that's why I needed to make sure that I put it in ascending order. And then I find the average of those two data points. The average of 14 and 16 is 15. And so my median for that third data set is 15. All right. The last measure of central tendency we are going to talk about is mode. Mode simply means the most frequently observed data point. So your data can have no mode. If everything is repeated the same number of times, then there is no mode. There has to be a most. There has to be a difference between them in order for there to be a mode. So if everything shows up twice, everything shows up once, you don't have a mode. In order to have a mode, there has to be some differences in the amounts. You can have one mode that is unimodal, two modes that is bimodal. We talked a little bit about that at the end of chapter 2. Or if you have more than two modes, there's not a technical term. They just become multimodal. So unimodal, bimodal, and then multimodal are the terms used to describe. Unimodal and bimodal are the most common types of graphs that you will see when doing research. And again, if you're doing research on something and you find out that there is more than one mode, typically that means you're looking at a population that has distinct subgroups within it. All right, so let's take a look at these 4 examples. There are 4 examples here. Take a second, try and find the mode or modes for each of those, and then unpause, and we'll come back together. All right, so this first one, there are 2 19s, there are 2 20s, and only one of the other ones. So 19 and 20 are the 2 modes. So this would be bimodal. On the next one, 20 is the only number that repeats. So that is our mode, and it is unimodal. This third one, there is no repetition. So there is no mode. Now, these were all in ascending order, which made it very easy to find. This last one is not. Now, you don't have to put things in ascending or descending order to find the mode. It can make your life easier, but you can also just kind of keep track and look to see as you're going. So I'm going to start going through. I see 1, 2, I see 3 5s. I only see 1 7. I see an 8. So there's 2 8s. There's a 9. 2 9s. So it looks like there's 3 5s, a couple 8s, a couple 9s, and then everything else is just 1. So 3 is the most common occurrence. So 5 is our mode. And again, this would be uni or unimodal. Just because the 5 and the 8 have more than one occurrence, they're not the most common value. That is the 5 with 3, and so they're not special. They don't get a title. Only the most frequently observed data point gets that mode label. Now, you cannot, like I said, you cannot have an average or a median when we're dealing with qualitative data. I can't find the average car color. I can't find the average handedness of someone. So if I go through and collect, are you right-handed or left-handed? I can't find an average of that, but I can find a mode of qualitative data. So I could see what the most common brand of car is in the parking lot, or what the most common shoe color is at Arapahoe High School. Those are things I can do. So mode can be used in qualitative data. Again, it is just whichever category has the highest frequency. So in this case, we are looking at injuries seen by a physical therapist in the last month. What is the most common injury? Go through and see if you can determine what the most common injury is for this physical therapist. So I have 3 knees. I have 1, 2, 3. Sorry, I have 3 necks. It looks like I have 4 knees, 1 back, a couple hips, a couple hands. So knee injuries are going to be the most common injury that this physical therapist has seen in the last month. This last part here, it says, read the explanation before or for what it means to be resistant. It can go, or you can read more in depth about it on page 122 and 123. I'll give you kind of a brief idea of what resistance means, and which statistics are or aren't resistant. So when you resist something, it means you like put up a fight. You don't want to change. So if something is resistant, it doesn't want to change. And so when we talk about a statistic being resistant, we're talking about how do new data points affect our previous data set. So let's say I have a data set that looks like this. Let's go 3, 4, 5, 6. 3, 4, 5, 6, 7. And we want to find the average of that data set. So I add everything up, I divide by 5, I get an average of 5, and I get a median of 5. Now, let's go one step further. Now I'm going to add in an additional data point. And this additional data point is going to be what's called an outlier. So it's going to be extremely far away from all of the other points that I have currently listed. So let's say I'm going to add the data point 100. It was supposed to be 10, but I typed it in incorrectly. I typed it in as 100. How is that going to affect my average? So let's find my new average with these additional, or that one additional data point. So now my average went from 5 and is now 20.83 repeating. However, my median, because my median doesn't care about how big that number is, it just cares that, okay, it's on the right-hand side of this data set. It's an even number now, so my median is now 5.5 because it's now an even data set, and so I average 5 and 6 together. This is an example of resistance. My average, because it takes into account not only how many data points, but what the value of those data points is, then the mean is not. It is not resistant. One data point changed my average from 5 to 20.83. So it quadrupled, more than quadrupled the average simply by adding one outlier point. So it's not resistant. It changes very quickly based on any single one point. However, my median was resistant. The median, sorry. The median is resistant because even though I had one big point I added in, it doesn't care about the value of that outlier. It only cares about the position of the points. So it didn't care if it was 100 or 1,000 or a million. It just cares about the fact that, oh, that's one more point, and this point happens to be on the right-hand side of my data. So I'm going to use the middle, which is 5 and 6, and I'm going to use that to find my median. If I had added a data point that was instead of 100, if that was a million, my median would still be the same. But my average would keep getting bigger and bigger and bigger as that outlier becomes more extreme. So that's the idea between resistance and non-resistance. All right, and now we're going to use that idea of resistance to talk more about the distribution shape and how that distribution shape is affected by or displays our measures of central tendency. How could we look at our measures of central tendency and talk about the shape of the graph that it would create? Or how can we look at the shape of the graph and then talk about those measures of central tendency? So first, we start with a nice, neat normal distribution. That's that smooth curve with one bump right in the middle. And with that, the mean, the median, and the mode are all roughly equal. All of them are going to fall in the middle of that graph. The mode is always where the highest part of the graph is, because as these are histogram graphs, the highest point represents the highest frequency. So the highest frequency is our mode. So our mode is always going to be the tallest part of the graph. But if it's symmetric, that also means the median and the mean are also in the middle. All right. When we have skewed left data, that data is skewed left. When we talked about this, this is something where there's no false cap. We talked about at the end of chapter 2. We talked about things involving money. We talked about housing prices or cars, where the bulk of cars or the bulk of houses are going to end up kind of in this price range here. But then, and I think in our example, we used between, or maybe we did cars, where cars were between like 10,000 and 100,000. But then you have some $1 million cars. Those $1 million cars are sticking out way over here. And that's going to affect which of our two measures of central tendency more. Is it going to affect our mean or the median more if we have outliers? Well, we talked about resistance, and we said mean is not resistant, which means anytime we have outliers, they're going to affect the mean more. So in this case, they want us to go through and kind of sort the mean, median, and mode. So this is going to be the mode because that's the highest part of the graph. And then our other two measures of central tendency get pulled to the right. Sorry if I think I may have been saying left skewed. I apologize for that. Right skewed. We're getting our measures of central tendency are getting stretched off to the right because of those outliers that have a much higher, much greater value than regular. And since the mean is not resistant, the mean changes more rapidly than the median. And then the middle one here is going to be median. So the mode is always going to be the highest part because that's where the most data is. And then if it's left skewed or right skewed, that means we're pulling the mean and the median in either of those directions. If it's right skewed, we're pulling the mean and median to the right. If it's left skewed, we're pulling those two to the left. And since the mean is not resistant, it gets pulled farther faster. So if we have a right skewed data set, we're going to pull the mean the furthest to the right. The median comes a little bit to the right, and then the mode stays at that highest part. This is also why, depending on what you're talking about, people can use statistics to tell different stories. In the example of something that's skewed right, I said things dealing with money is skewed right. One of the things that deals with money that's a big talking point is income. Income is money, and money can be skewed right. So during the pandemic, there was a lot of articles coming out about how much money Amazon was making, but also about it was making so much money, but it wasn't paying its employees this much money. And there's really horrible, awful working conditions, a bunch of stuff like that. And there were two sides to this argument, obviously, because there are two sides to all arguments. If there's not two sides, it's not an argument. And one of them came out and said, Amazon pays its people very good money. The average salary of an Amazon employee is $60,000 to $70,000, which is a really decent income. I would be happy making that much money, or I am happy making that much money. And so they're like, look at that. See, Amazon isn't cheap. It pays its employees an average of $60,000 to $70,000. Good job, Amazon. Then there's other people that said, yeah, I don't care about that. The median income of an Amazon employee is between $30,000 and $35,000. That's a huge difference. That's almost half, or that is approximately half of what the average income is. And neither person was lying. They weren't wrong. They were simply using a different statistic to tell their side of the story. And the reason there was such a large difference between the median and the average is because money is skewed right. So while most employees at Amazon may make between $30,000 and $35,000, can you think of an employee that makes substantially more than that? The answer to that question would be Jeff Bezos. He is worth billions of dollars. His, I think during the pandemic, he made an additional like 15 or $20 billion. It is some crazy amount of money. But if you average all Amazon employees and you include the fact that he makes hundreds of millions of dollars a year, or $1 billion a year, whatever it is during the pandemic, that is an outlier. That is going to pull up everyone else, and it's going to make the average look really good because he makes so much money. Now, whether you think that is accurate or a good way to describe the amount of money that the typical Amazon employee makes, that's up for debate. But neither person or neither group would be lying if they used either of those statistics. It is simply them trying to tell you a story and using numbers to get their point across, their side. And then we do the same thing on the other side. This is skewed left. And again, the mode is always the peak. The mean always gets pulled the furthest. And the median, just like in our data set, our median is always in the middle of our mean and our mode. It's either equal to, or it'll be in the middle of those three measures of central tendency. All right, that is the end of 3.1. 3.2, we'll be talking about how we talk about the spread of the data.